Determine and classify the poles of f of z is equal to 1 over z times 1 minus z squared. Okay, so again, the poles are going to occur when we're dividing by 0. And we've just got a polynomial here, and I noticed that 1 minus z squared can be factorized into linear factors. So it's 1 over z, 1 minus z, 1 plus z. So yeah, and so we have singularities at 0, 1, and -1. And they're all simple poles because, you know, essentially because like they're all, um, they all, each kind of factor here, we have it's 1 over z times 1 over 1 minus z times 1 over 1 plus z. Right? Each factor is responsible for one separate pole, right? So there's poles at, like, as I said, 0, -1, and 1, right? So 1 over z, okay, has a pole at 0, but then this part here, it's, doesn't have any zeros or singularities at 0, right? So it doesn't contribute at all. It doesn't modify the simple pole that 1 over z has, and that goes for all the other ones. So yeah, this one's nice and easy. So then f of z has simple poles at z equals 0, 1, and -1. That's it. Okay, B. Calculate the residue at each pole. Let me actually go to a new page. Go. Okay, so what is the residue? So definition. The residue. Okay. So we need, what do we have? Let f from U to C. Should say, sorry. Be differentiable on a punctured disk. BR Z naught take away Z naught. Um, and we know has a Laurent expansion. So have Laurent expansion, f of z equals, let me just call it n equals minus infinity to infinity, Cn z minus z naught to the n, okay? Then the residue of f at z naught is um is we denote it res f z naught, and that's simply equal to the -1 coefficient in the expansion. So the coefficient attached to yeah, z minus z naught to the -1. So this seems very arbitrary, but in fact, it's yeah, it's crucial. So it will become clear why it's called a residue and why it's important later. For now, there it is. So how to calculate it? Well, in this case, um, well, you just use this theorem. If f has a simple pole at z naught, then the residue of f at z naught is equal to the limit as z tends to z naught of z minus z naught times f of z. Okay, but why is that? Let me give you a little proof. It's very, very simple. Well, basically, in this, punctured disk around z naught, right? F of z looks like, well, because it has a simple pole, it starts, the Laurent expansion starts with, c to the -1, z minus z naught, -1 plus c naught plus c1, z minus z naught, etc., right? So if I then just multiply by z minus z naught, then I'll get c to the -1 now as kind of my constant term in this expression. And then if I then let z tend to z naught, all of those terms will go to 0, and we'll just get left with c -1. Yeah. And you might ask, oh, but how, this is an infinite number of terms. How can you just plug in, that's a bit weird. And I suppose it is. But I mean, uh, like essentially like z minus z naught f of z now has a Taylor series. So this is like a continuous, this is a continuous function. Um, or rather, I know f of z is not defined at z naught. So technically this is not defined at z naught, but essentially this has a removable singularity, right? Um, it could be this formula could be used to extend the definition of that to z naught, and then we can just plug in z naught. So anyway, that just to give you an idea. Uh, yeah. Okay. So we're gonna use that to calculate the residue at each pole. So by the way, um, this is known this is known as the cover up rule. Uh, and why you know why is that? Well, because in this case, for example, recall, so f of z is equal to 1 over z times 1 minus z times 1 plus z. So the residue of, for example, the residue of f at 0, right? 0 was a root, so that's the limit as z tends to 0 of z minus z naught. So z naught is 0, so that's just z times f of z, which is this. So what happens is here, these z's cancel, and then we take taking the limit as z tends to 0, well, we can just plug in 0. So we just get 1 over 1 minus 0, 1 plus 0. So we just get 1. So that's why it's called the cover up rule, because yeah, essentially like it comes down to kind of, if I want the residue at 0, it comes down to like covering up this z, right? That's kind of responsible for the pole at 0, and then plugging in 0 into the rest of the expression. Now, careful though, because um, it, you can't, you might think, oh, sorry, you might think, okay, then if I want the residue at 1, then I can just cover up this term and then plug in 1. However, if I actually run the definition through, then you see that, okay, basically like this should cancel with that, but it doesn't cancel exactly, right? Because this is minus that. So those simplify to a -1. And so if we plug in, if we now plug in 1, then we'll get -1/2. Excuse me. Right, so careful that you can only cover up a term if it looks like exactly like z minus z naught, right? Not z naught minus z or a multiple of z minus z naught, right? So if you wanted to kind of very quickly use the cover up rule, you would have to just kind of manipulate the expression so that um everything looks like z minus z naught, z minus 0, z minus 1, z plus 1, right? Um, so now a little bit more quickly, the residue at -1, this is the z minus z naught, where z naught is equal to -1. I cover it up, and if I plug in -1, I see that I get -1/2 again. Let me be careful. -1 over -1 times -1 minus 1. That's a lot of negatives, but yeah, we do get 1 over -2, or -1 over 2. If you want to be careful, you can just, do the limits. Yeah, cool. Okay. C. Hence, use Cauchy's residue theorem to evaluate the integral of f of z dz over the contour gamma for two contours. Okay, so what is Cauchy's residue theorem? So this is probably the crowning theorem of like a introductory complex analysis course. Really core theorem. Cauchy's residue. So let U be a simply connected domain. So a simply connected domain is uh, is basically so it's a connected domain, so like one that's made of only one piece, but in particular, it has no holes whatsoever, right? So for example, like if I kind of made it into if I put a hole in this and made it into like this ring or whatever, like it would still be connected, it would still be one piece, but it wouldn't be simply connected because there's a hole in there. So think of it as just it's a blob, right? Some kind of blob. Or you can think of a disk, for example, right? It's a simply connected domain. Okay. So let U be a simply connected domain. And suppose that um, F from U to from U with let's see, like Z0, Z1, blah blah blah, up to Zn um to C is holomorphic, right? So differentiable on that whole domain. So I have a simply connected domain, and then you remove a finite set of singularities, right? So F is differentiable on a simply connected domain, except for a finite set of singularities. It's holomorphic. Then, oh, and let gamma be. There's a fair few ways of stating this theorem, but I'll state it in perhaps the most simple way, one of the most simple ways you can state it. So let gamma be a simple um, positively oriented closed contour in U, right? So what does it mean? Simple, positively oriented, and closed. It just means that um, it's so closed. So a contour. Okay, we haven't talked about contours at all yet. So a contour is basically a parametrized curve, right? So something like that. Um, Parameterized by a parameter like t. And so, so that's like gamma of t or whatever, right? And as t, as t varies, let me get this. So, um, so that's a contour. It's closed means that it kind of its starting and end points are the same, right? And positively oriented means it actually runs counterclockwise, and simple means it only runs once, right? So as t varies in the range that is prescribed, we go around the loop once and we stop where we started. We don't go twice around. So simple, positively oriented, closed contour in U. All right. Then the integral over gamma of f of z dz is equal to 2 pi I times the sum of the residues of f and zi, where we the sum runs over zi inside gamma, right? This is not very formal, but uh, if if I label my Z's here, Z0, Z2, Z3, Z4, Z5, Z6, right? Then um ooh, I should say that this contour should not go through the singularities, though it's not very shouldn't be a problem in anything that we do here. Yeah, so for example, like here, the integral of f over this contour gamma um, is going to be 2 pi I times the sum of the residues at Z1, Z2, Z4, and Z6. Okie dokie. Okay, so what do we have? So what we have is we have a function f and we had poles. This was a function that was differentiable everywhere except at 3 poles, -1, 0, and 1. Okay. Okay. And so, and in I, gamma, let's call it gamma 1. Okay, gamma 1 of t is 9e to the it, defined as 9e to the it, and t runs in 0 to 2 pi. So 9e to the it, well, that just looks like a number, like a complex number in polar form with um with modulus 9 and argument t, right? And then t runs between anything between 0 and 2 pi. So okay, maybe I'll rewrite my drawing ever so slightly because just to put the singularities a little bit closer together. This is not going to be to scale at all. But anyway, 9e to the it, that's that's the that just parametrizes the that just parametrizes a circle of radius 9 centered at 0. Okay. Right? Basically, this runs through all of the complex numbers of modulus 9, right? Because here the argument is essentially arbitrary, right? It starts and ends here. It runs anti-clockwise, right? Um, it runs anti-clockwise. It's closed. It goes around once. So it's a simple positively oriented closed contour. And it contains inside of it the 3 singularities. Okay. So yeah. So in this case, by Cauchy's residue theorem, remember, write it here. F of z was just this, right? That's equal to 2 pi I times the sum of the sum of the residues. So that's the residue at 0, at 1, n at -1. And the residue at 0 was 1. And then at 1 and -1, it was -1/2. So we're going to get 0 in this case. Cool. Then in 2, so that's gamma 1 there. So gamma 2 is defined as a quarter e to the it, t running in 0 to 2 pi. So that's just going to be uh, a circle of radius a quarter centered at 0. Quarter. So this one only contains singularity 0. So it's 2 pi I times simply just the residue of f at 0, which is 1. So it's 2 pi I.